What is the wave function collapse conceptual challenge? Imagine watching a coin spin in the air, not knowing if it's heads or tails until it lands. That's similar to what happens with particles in quantum physics. The wave function is like that spinning coin, showing all possible outcomes at once. When we measure the particle, it suddenly chooses a specific state. This is called wave function collapse. But why does this happen? That's where the big questions begin. In quantum mechanics, particles like electrons and photons are described by a wave function. This wave function is a mathematical way to show all the possible places or states a particle could be in. It's like a map of probabilities. The particle can be in many states at the same time, a situation called superposition. Think of it as a coin being both heads and tails at once until you look. When you measure the particle, the wave function collapses, and the particle becomes one definite state. The challenge is understanding what causes this collapse. Some say it happens because of the act of measurement itself. This idea is part of the Copenhagen interpretation, which suggests that the observer plays a special role. But that raises questions about whether the observer influences reality or just observes what's already there. It's a tricky concept because it makes us wonder if reality depends on us looking at it. Another challenge is the randomness of the collapse. The wave function predicts the likelihood of each outcome, but it doesn't say which one will happen. It's like rolling dice. You know the chances, but not the result. Einstein famously disliked this randomness, calling it God playing dice. He believed there might be hidden rules we don't yet understand. Different interpretations try to explain this puzzle. The many worlds interpretation suggests that all possible outcomes happen, but in separate branches of the universe. So, when a measurement occurs, the universe splits into multiple versions, each with a different result. This idea avoids the randomness problem but introduces the concept of countless parallel worlds. In practical terms, wave function collapse is essential for quantum technology. Quantum computers relying on superpositions to perform many calculations at once. When a measurement is made, the wave function collapses, giving us a specific answer. For example, in quantum algorithms like Grover's search, the goal is to manipulate superpositions so that the collapse reveals the correct solution with high probability. Understanding wave function collapse helps us develop better quantum devices and interpret their results. It's a core part of quantum mechanics that raises fascinating questions about how nature works at the smallest scales. While it's still a puzzle, it's also what makes quantum physics so exciting and full of potential.